review for you the math exam from 2015, so that's last year's Math 1B exam. We'll do mostly the questions 3 and 4 from the 1231 exam, although I've had a request from a 1241 question from 2015 as well, and I'll do that at the end. We will be finished in time for the Melbourne Cup. Those of you who need to go and watch a horse race will be able to go watch the horse race. Don't you worry about that. So, I'm joined here with Josh. Josh, this is your question. Again, we'll alternate questions. Josh will do this one, and then I will do mostly help.
You go ghostly down here.
Yeah. Cool.
Right.
All right. Josh, you're up.
We seem to be live.
Cool.
All right. Actually, this problem will be kind of familiar if you saw the live stream for test 2 of calculus, because we also there talked about exact equations. So this question wants me to show that this differential equation is exact, and then, well, use that information to solve the differential equation. So and this is actually how I would start this question, is remind myself what it means to be exact. So this ODE will be exact if there is an f x y such that df dx, that's going to be equal to this term here. So some people like to rewrite this by moving a dx over here, but I was going to say df dx is this term, and if this f I'm talking about has df dy equal to this, so that's going to be 3 x squared y squared. So what I'm saying is, yeah, so this is going to be what you usually call f of x. This term is f of y. And there's actually an easy way to check that this is true, is to check whether or not these are compatible, to check whether the cross derivative you get from looking at these two is actually the same. So I might just work here. So to check, calculate, and so calculate what you get if you did df dx dy, which I mean d dx of what supposedly is this, so which is d dx of 3x squared y squared. Well, y is a constant as far as this partial derivative is concerned, so I'm just going to take the derivative of x squared, 2x from that. So I go 3 times 2 is 6x y squared. So that's what I get from looking at this term. Yeah, this is accurate information. And the other one, if it was dy dx, which is d dy of df dx, well, that's d dy of this 2x y cubed plus 4. Well, this is a constant, it's 0. Ignoring the x, since we're taking a derivative with respect to y, this will give me, it'll give me just a 3 coming out, and I get 3 times 2, 6x y squared, which is the same as above. So these two things are equal, and so I'm just going to draw my conclusion. Hence, the differential equation is exact. That's what I've shown. So if this is exact, then, well, it is exact. So now I know I can find such an f. So I'm going to use this information to find that f. Alright. So I'm going to give these some numbers so I can refer to them a little bit later. I'm going to call this equation 1, and this equation 2. So this one will tell me, this one I can integrate with respect to x, and it'll tell me something about f. Well, it'll tell me something about f, and I'm going to do a bit more information. So integrating 1 with respect to x, so I'm integrating with respect to x, I get the following information. I get that this f, whatever it is, well, integrate this term with respect to x, the x goes to x squared, you divide by 2, so you get an x squared y cubed, you integrate the 4, you get a 4x, and now, because this was a partial derivative, anything which was a function of y wouldn't have turned up in this calculation, so there's a lot of room for what's left over. What's left over could just be any function of y. So we need to work out now what this function is. So it's a function just of y, and I should be able to get some information about it. Okay. So this is where 2 is going to come in. So let's just differentiate this and compare it to 2. So differentiating and comparing to equation 2 gives, we'll have df dy, which will be equal to 3x squared y squared. Well, this thing is a function of x, so it will just vanish. And this will just be the derivative of whatever function, that function I don't quite know yet. And they'll have to equal what I have over there, so they'll have to equal 3x squared y squared. So now I have this information. And note, c is a function of one variable only. It's only a function of y. So this notation makes sense. It's just a derivative of one variable. Right. So I almost know what my f is. I just need to put those two pieces of information. I just need to look at this and see what it tells me about the derivative of c. Well, you can just easily compare both sides of this, just subtract one from the other. You'll see that, hence, the derivative of this unknown function c is just equal to 0, which just means that actually this unknown function is a constant, i.e. c of y is a constant. So then I know my f is just going to be this term plus a constant term, and when I draw that all together to get my final solution, well, I get, so the solution to the, I'll just say ODE, ordinary differential equation, is fx y equal to x squared y cubed plus 4 times x. That constant I'm actually not going to write down because I'm going to write this as equal to d for the constant d. There is always an arbitrary constant when you're looking at the solution of an exact equation, so I'll just draw my other constant inside there and hide it. Right. So, do you have any comments, Daniel? He'll be back. So I think one thing I might have done differently if I was doing this again in a test is I was just assuming that these really were going to be, well, I could give these names like H and G. I think that's a fairly typical thing to do, but I think I'm happy writing it out this way. I'm saying, if this is going to work, this is what I should have. So do you have any comments?
I would have done H and G.
Right.
I think that's the way it's done in the book, and this subscript. Well, I see what you're saying, but it kind of presumes it is actually exact.
Yes.
And then, which it ends up being, but you don't know that. Technically, you don't know that just yet.
Yes. So you might want to redo that, call those H and G, just to, so that'll be
Cool.
H. I think this one would be G. So, yeah.
Cool.
Okay.
All right, next question.
There were some comments in the chat about the audio. If some more audio adjustment is necessary, just let me know. Also, some of you in the chat were taking bets on what shirt I was going to wear. You should know better than to bet with the person who's teaching you probability. Cool. I get an easy question. Find the general solution to the differential equation, blah, second order non-homogeneous differential equation. The first thing you do, always the first thing you do, is solve the homogeneous equation. You solve this equation, just whatever that means, whatever junk they put here, ignore it, you need to solve this first. And the solutions are easy to find. Again, you wouldn't necessarily write this in an exam, but I can't help myself. The solutions to the homogeneous equation are this, where the lambdas are the solution to this equation, and I can just solve this by saying that's lambda minus 2, lambda minus 4. So lambda is equal to 2 or 4, and hence y of t. And hence this is the solution to the homogeneous equation. So many of you will just go straight down to this part. You may just go straight to this, and that's entirely appropriate. If you just want to write this as your answer, that's fine. Now we're going to solve the non-homogeneous equation. And now you have to put back the junk that you got rid of initially. Now, The reason you need to solve the homogeneous equation first is because to solve the non-homogeneous equation, you need to have solutions which are non-homogeneous, which means you need to know what things you're supposed to avoid. You have to avoid e to the 2t and e to the 4t. Unfortunately, this is nothing like an e to the 2t or e to the 4t, so we're going to guess just whatever t. I should have used t's. I meant t's instead of x's. X's instead of t's. The thing you're supposed to guess here is a degree 1 polynomial. So you guess a degree 1 polynomial as your non-homogeneous solution. Again, the point is you guess something that is not homogeneous. If what you're given does look like a homogeneous solution, just keep multiplying through by an x until it's no longer homogeneous. So here we have it easy. If this is a solution to this equation, then it should satisfy that equation. And I compute yp prime, yp double prime, and I throw it all back into this equation. Yp double prime minus 6 yp. And that's 0 minus 6a plus 8 equals 16x minus 4. And I can simplify this side, that's 8ax plus 8b minus 6a equals 16x minus 4. And now I just need to find out what the a and b are. And I can compare coefficients of x. If the coefficient of x here is 8a, the coefficient of x here is 16, so 8a must be 16. And I can compare coefficients of x to the 0, so that's x to the 1. This one can be x to the 0, and that tells me that 8b minus 6a is equal to negative 4. And I know a already is 2, so this is minus 12, which I'll take over there. So that's 8b is equal to 8, so b equals 1. And hence the solution is, well, the general solution, just right up here. The general solution is just the homogeneous solution plus the particular solution. So a was 2, so that's 2x plus b. Done. Homogeneous solution, particular solution. Josh.
So yeah, I mean, this is a fairly standard problem, and the technique for solving it is fairly standard. So always solve homogeneous first. I mean, you always need to solve homogeneous first. You don't know what issues are going to come up when you try and match your particular solution. So yes, you do. You want to check first whether or not you're going to have any problems. You don't want to just go straight to particular and try and do that.
I mean, with this one we can be a bit cheeky because we know we're not going to get problems with this. This is a polynomial. If you get an exponential or something with sines and causes, then you might have to think about it. But for polynomial, the solutions aren't going to interfere with one another.
You could have well, in this case, there's no zero. There's no characteristic solution. There's no zero for that characteristic equation, so you won't get any constants. All right. Should we move on to the next one? I think there's not much to say about this. So this is a fairly short question in terms of the length of the question, and it should be fairly quick to answer this one too. So now this is one for 1231. So so here when it's asking for the interval of convergence, it is explicitly asking for the open interval of convergence. I don't care what's happening at the endpoints of the interval. I just want that open interval. And actually, the technique for answering these sort of questions is typically always the same. You're going to use the ratio test to work out where this is going to be convergent and where this is going to be divergent, and, well, you have your answer. So let me just set some notation first. Let a subscript k be this term here. It's going to be the 2x minus 7 to the power of k over k squared. So just that's one that be. And let's consider what we get if we take the ratio of these two terms. So I'm going to look at the ratio of the next term, ak plus 1, over ak. So ak plus 1, let's take this. It's 2x minus 7 to the k plus 1 over k plus 1 squared. So I'm just looking for the k's and replacing those k's with k plus 1. Now, I can put this term underneath, but that's not the way I would write this out. I would actually take this, flip it over, and put it beside it. So this is trying to avoid those double-decker fractions. So yeah, this term is now on the top here, and you'll have a 2x minus a 7. For the k, well, we can simplify this. Most of these powers of k will cancel out pretty much everything here to give you a 2x minus 7. And I'm actually going to collect these other k terms together to be k squared over k plus 1 squared. And my intuition is, well, leading order, when k gets very large, this behaves like k squared. And this bottom part behaves like k squared plus something which won't actually matter as much as k squared. So I expect this to go to 1, and I can make that a bit more obvious just by writing it as 2x minus 7. I'm going to expand out the k plus 1 squared, and I'm actually going to multiply the top and the bottom by 1 over k squared. And if you do that, you'll find that this is actually the same as 1 plus 2 over k plus 1 over k squared. So here I've just expanded this bottom term, and I have divided the top and the bottom by k squared, and you can see that this definitely tends to 2x minus 7 as we let k go off to infinity. So what we need that this term in absolute value will be, well, this term should have magnitude less than 1. That's what's going to give us convergence. So for convergence, by the ratio test that is, I might say that by the ratio test, me that that term had magnitude less than 1, and you can write that as the term being between -1 and 1. So this is saying that term there has to be between -1 and 1 if this is going to converge. If it's strictly outside, well no, if you get strictly bigger than 1, so magnitude strictly bigger than 1, you definitely have divergence. And this is nice because now I can just manipulate this to find that interval. So first things, I'm just going to take everything in these inequalities and shift them over by 7. So this will keep things nice. This will preserve the inequalities. So this plus 7 is 6, less than 2x, less than 8. And, well, if I divide everything here by 2, the order of these numbers doesn't change. So they squash together, but you still have the same inequality. So, I might use a more mathematical symbol here. This is going to be true if and only if. This is true, which is true if and only if 3 will be less than x, will be less than 4. And I might just conclude what that means, i.e. the open interval of convergence is, well, it's going to be everything between 3 and 4, and I'm not including 3 and 4 because the question asked me just for the open interval. So, Daniel?
The only thing I'd add to this is that the ratio test talks about the absolute value of this thing being less than 1.
Yes.
So that's where the absolute values come from. It's actually from the ratio test, which says that you want that. And then of course as k goes to infinity, this thing approaches essentially the absolute value of 2x minus 7, and you want that to be less than 1, which is where this comes from. So yeah, I just add some absolute values to that.
Yeah, you do have to be careful. I was a little bit lazy with that and just sort of, yeah. So if you add the absolute values here, so this thing less than 1, that translates into this condition.
Alright, I think we need to pick up the pace.
Right, okay.
So maybe we'll have to take off our educator hats and just get on our exam hats.
Right.
Right, use some test to determine if the series converge. That's a K4. Right, well this one, I can see it looks something like k to the power 1 on k to the 3. So this one to me seems like a 1 on k to the 3, which I know converges. This one here looks like well, these terms are approaching 1. So my feeling is this one converges because it's the p-test, and this one should diverge by the nth term test. So that's my plan. I want to compare this to 1 on k to the 3, and I'm suspecting that this will be less than 1 on k to the 3. So I'm making some kind of comparison between this thing and 1 k to the 3. And I want this to be bigger so I can say that this thing converges and therefore this thing must converge. Here I am with my educator hat on again. I should really just get with the question. I'm going to put that up there and that up there. So that's k to the 4 is the small to k to the 4 plus 1. And here I've implicitly assumed that k is greater than 0. If k was negative, then this would have split the inequality. And 0 is less than or equal to 1. I like doing things this way. It looks like you're just an absolute genius at math. This is the thing you want, and you start off with an innocent-looking statement like 0 is less than or equal to 1, and then you arrive at exactly what you want to. So, since that's the case, then the sum, so every one of these terms is less than or equal to every one of those terms, so the sum from k equals 1 to infinity of these terms is less than or equal to the sum of all those terms. And this converges. Good. You don't need to say what the p-test is, you just write converges by p-test. Part B. This thing, my feeling is, it can't possibly converge, because these terms are approaching 1. Okay. -2, since I might call it the kth term test. It's nth term test that, whatever, kth the kth term test. The idea here is that if the AKs are not approaching 0, then the thing can't converge. You need it to go to 0 to have any possible chance of converging. Josh?
Yeah, so with these questions, do stop and think about, just have a brief pause, think, okay, why? What is my reason for thinking convergence or divergence? So here, this was actually quite simple, yeah. The terms aren't going to 0, that's a strictly necessary condition. This one, well, it's nice that actually this is strictly less than 1 over k cubed, so you get that one quite quickly, and this is nice. That you sort of, yeah. Now that I come and look at it after he's done it, I can't tell that he hasn't actually worked this out from that principle. He's actually, so it's a nice little trick.
The idea is you've got a lot of tests for convergence or divergence, and you need some kind of quick way of determining which one of those tests you're going to do. Knowing if this is going to converge or diverge is a great way to split your tests, because this one only tells you when it diverges.
Yes.
And yeah, anyway, more questions.
So you guys are open for those different. Alright, so this is one of these maple questions that can appear in your final exam. So they've given you the output of some maple commands, and you should be able to find the answer for whatever this question is. So here, we're given a function which is the sine of x cubed, and we're just told, give me the value of the ninth derivative of f at x equals 0, and that should be somehow apparent from the commands they've done here. So, firstly, let's note, so we have a Taylor series of this function g. G is the derivative of f, and after a slight bit of panic, I realized what I really need to do is realize that the ninth derivative of f is the same, well, that's just going to be the 8th derivative of g. So I know what I'm looking for. I'm looking for the 8th derivative of g at x equals 0. Now, this is nice because the Taylor series does encode all those derivatives. Well, the Taylor series at 0 encodes all the derivatives at 0. So somehow this is telling me almost exactly what I need to know just in this term here, the power of 8. So rather than try and manipulate these things in my head, I'm just going to write out what this is trying to tell me. So, and the Taylor series gives, well, I'm looking at this term here. This term is supposed to be the 8th derivative of g at 0 divided by 8 factorial. And I might just include that x to the 8 as well, and that's supposed to be equal to this term, the minus 3 over 2 x to the 8. So the Taylor series tells me that this term here, which has got the number I really want inside it, will be related to this. Of course, I don't need those x to the 8s, so let's just cancel those out. And that pretty much gives me my answer. So hence, the 9th derivative of f at 0, which I told you should be the same as the 8th derivative at 0, is just going to be this number multiplied by that. So that'll be minus 3 over 2 times 8 factorial, and that's all I'm going to do. I'm not going to try and simplify that number. So that's the answer. Right. Any
Nice.
comments?
No, it's perfect. You just lift off the answer from the maple session.
Yep.
That's what you should expect to do when you find the maple session.
Yeah. Maybe a little bit of manipulation, but not much. Okay.
Okay, so here's some crazy looking question. You've got some function between a and b. You've got its arc length and the area bounded by the graph and the x-axis. So I said I'm going to do this in a kind of exam condition way with my exam hat on and not my teacher hat on, and I'm still going to draw a graph of whatever this is. That's important. Even in an exam, I would draw a graph of what this is. So I've got some function like hyperbolic cos, like this. And between 2 points A and B, I want to make some kind of comparison between the length of the curve, which is this thing. So this length here is L, that's A, and that's B. And I also want to know something about the area under the curve. And it seems very strange. I mean, yeah, okay, this is an area, this is like units squared, and this is a single unit. So shell for a moment. Don't let details like that bother you. This is going to be some number, disregard the units. This is going to be some other number, disregard the units. We're just going to check that that number is that number. Good. Well, we need the formula for arc length. L is the integral between A and B of the square root of plus. Sorry, that's H prime. This is the formula for arc length. You will need to have this at your fingertips to be able to do this exam. So this is the integral between A and B of the square root. One, well, H prime is just hyperbolic sine. Squared x dx, and that's A, B, that's the square root of, now I can never remember how this goes, so I'll just do a quick calculation over here. It's cos h squared x minus sine. That's the way the identity goes for hyperbolic trig, so this is just cos h squared x dx, which is and you move on. You don't bother yourself with the fact that those are different units. You just remember the formula, turn the handle, it ends up being the arc length. It ends up being the area under the curve. So, it looked like a strange question, but it didn't end up being so strange once you remembered that. And always picture. Picture will help you piece together all the different things that are happening within the question. So, Josh.
So maybe just one piece of justification for a step here. Cosh is a positive function, so this is the absolute value of cosh, because you've taken the square root of the square, but it's a positive number, so you will always get cosh back. So that actually might be something you want to state. Just you want to be.
That would have been a good thing to state.
So you could, yeah. So you could have put just a comment here, since cosh is positive. All right.
I think having a diagram might have alerted you to that. If cosh did, or if the function was negative, then at least you had a diagram of it, and that would have hopefully alerted you to whatever subtleties were going on over here.
One very nice thing about this, no integral was ever computed. So that's a nice way to do it without
Yeah. Computing integrals without actually computing anything.
Right, so this was actually the final question on last session's exam in question 4. And it's really testing your understanding of convergent series. So they say, okay, we give you a series. This is a series of positive real numbers, so these AN are all going to be positive. And you have to explain to me why there's going to be, at some point, some value of m, once I go beyond that, all of these values are going to be less than 1. So once n is greater than some m, there's going to be some m where eventually I know, once I go past that point, everything I have left over, every an is less than 1. And, well, that's just because that's the nth term test. If someone tells you you have a convergent series, that means the terms must tend to 0. So, yeah, so the kth term test, I think it might be called. So, since the series is convergent, kth or nth? Anyway, kth term.
We're doing, well, your index is n here, so
Okay,
maybe we should call it the n term.
So that's called the nth term test. Says that, well, it just says that an tends to 0, as n tends to infinity. And, well, the definition of this is that for any bound you wish to push, so any epsilon value, eventually the difference between this and 0 will be less than epsilon. So I might just say it that way. For epsilon equal to 1, big epsilon, but never mind, we are guaranteed that, well, that an, or I should say the difference between this and 0 is less than 1. How will I state that? After n is greater than m. That's just a sum m. That's what this statement means. So this works for any epsilon, but I only really care that epsilon is equal to 1. So this works for some index m. And well, these are all positive numbers, so that is exactly the same statement as saying n is less than 1 for n greater than this m. Alright, so that's, yeah, so I know this is going to happen. This gives me this specific fact. It gives me a lot more facts actually, but I'm just picking out the one that really matters to me. Alright. So, now we're told to prove that hence, if we try to sum up the squares of these numbers, then we also have a convergent series. And the hence is telling me what I've done is a key to this. So this m is somehow very helpful in showing this. And you can easily see why. So since since the sum from n equals 1 to infinity of an squared, well, let's just break that into two sums. It's going to be sum from n equals 1 up to this m value I know about of an squared, plus the sum from that point onwards, so from n taking the next term up to infinity of an squared. And yeah, I've just taken this and split it up into two pieces, something which, to be honest, I don't really know too much about, and something which I do have some information about. So, well, if you take a number, so here, so maybe I'll just put a little sub-fact here. So note an squared will then be less than an for n greater than n. If you take a number which is less than 1 and square it, it definitely gets smaller. That's what I'm saying here. You could just say multiply this by an, that gives you the fact. So just note this fact. So that means this, well, these terms are going to be less than if I just had put the an's there. So this will be less than or equal to, strictly less than I think, an squared plus the sum from n equals m plus 1 to infinity of just an. Now there's a very nice theorem that tells you if you have two series, you're summing up two series of positive terms, and one has terms which are always less than the other, then, well, either the convergent one will force convergence on the smaller one, or the divergent one will force divergence on the larger one. So if the smaller one's divergent, it pushes off the other one to be divergent too. So here we have that these are just sums of positive numbers, and they're going to be less than a convergent series, so that actually proves convergence. And I think it might be worth actually stating that as a general fact before I use it. So note, if AK and BK, well actually let's say, do it again. So we have positive numbers, and I have that AK is less than BK, or less than or equal to BK. So if this is true, and that the sum of k equals 1 to infinity of bk is convergent, so if I have these two facts, then the sum from k equals 1 to infinity of ak must also converge. Right. So yeah, so this is a convergent sum bounding this sum, and these terms are all positive. So I might give this a name. Let's call that factor little 1. So by 1, the sum from n equals 1 to infinity of an squared must also converge. So I have actually forgotten something. I forgot to state the fact on paper that this is convergent. I told you that, but I should say here, which is convergent. I think it is important to state that. You might not need to state this, but it's important you know what's going on. Any comments, Daniel?
There's a lot of comments in the chat about how this is a very hard question.
This is a very hard question. This is probably going to distinguish between those who really, really understand the material and,
well, this is covered like Math 1A.
Yeah.
So not so much understand. Well, yes, understand the material, but also can remember that far back to the epsilon m definition of a limit.
Right.
Maybe there's a way we could do this. Like, say you get a question like this in your exam. Yes, maybe you've forgotten the epsilon m definition of a limit, but perhaps this can still be done, even though you know that. Yeah, so maybe you just burn this part of the question because you've forgotten it, but you can still achieve the marks for this side of the question. So there might be a way to do that. Let's come back to that in an exam. So you're in an exam. There's some question that's going to kill you. Put a circle around it, move on. You don't have time to go through and just think about what would be a lovely method in this, and we'll do that now. So if we have time before 3 o'clock, we'll come back to this. But just to exemplify what you should be doing. It's a hard question. We're going to burn that. Maybe we'll come back and get some marks for this. We'll see.
Yes. Would you like to do the requested problem or these other ones?
I should probably do the request problem. No. Yeah, I'll do the request problem. No. Request problem's a bit freaky, and I think we need to alternate between freaky things and pleasant things. So let's do a pleasant thing. It's like a nice piece of music which alternates between periods of intensity and periods of calm. Let's do something to promote calm.
Okay. This is actually another one of my questions.
Cool.
So I'll do this one, but this won't be nearly as tricky as the last one. In fact, this will be almost almost algorithmic. Should be fairly algorithmic actually. All right, so we're given a 2x2 matrix, and the question is find the eigenvalues and the eigenvectors. Well, so yes, first thing to do, we need those eigenvalues, find those eigenvectors. Let's do wet. And for a 2x2 matrix, the easiest way to find the eigenvalues is just to calculate the characteristic equation. Well, that's even more obvious, but just calculate the characteristic equation and then you can find the roots. So the characteristic polynomial of A is, well, it's going to be the determinant of A minus lambda times I, which is the determinant of this matrix with lambda subtracted off the main diagonal. So there should be no surprises there. And that is just going to be product of these two diagonal terms minus the product of the off diagonal terms. So this becomes a minus 1 times minus 2, so it's a plus 2. Alright, so let me just do this slowly so I make no mistakes. I will get a 4. I will get a, well, let's say a minus 4 lambda. I will get a minus lambda. I already made a mistake. Minus 4 lambda. And a plus lambda squared plus 2. Just move that around. You'll get lambda squared minus 5 lambda, 4 and 2 makes 6. And, well, in this case the roots are obvious, so for those of you who can spot them, that's nice. I'm still going to use the quadratic equation, because it's always where I fall back on when I forget. So, yeah, this has roots. Lambda is equal to 5 plus or minus the square root of 20. 5, 4 times 6 is 24, minus 24. 2 times 8 is just a 2. So you should know the characteristic equation, you should know the quadratic formula. This is nice, it becomes a 1, so 5 plus and minus 1 on 2 is the same as either 6 on 2 or 4 on 2, which is 3 or 2. So those are the eigenvalues. You know the eigenvalues are going to be 3 or 2. And the next calculation I'm going to do is going to verify this, because if these are correct, it's definitely going to show up in the next step. Alright, what do we do for lambda equals 3? So for lambda equals 3, we consider, well, we're just going to take this, subtract 3 off the diagonal, so 4 minus 3 is 1, that just stays as it is, I don't change that, and I subtract 3 to get that, and I'm trying to solve these equations, and I think a lot of people didn't like it some people didn't like it last time when I just solved this without work, although here I can see these are exactly the same equations. I still will do one step, so I'll take row 2 equal to row 2 minus row 1, then I get the row reduced matrix, like so. So I have my one leading entry, I get a parameter here, and because there is a non-zero solution, I know I've done the right thing. So hence, the eigenvectors for lambda equals 3 are, well, they're just going to be vectors of the form some constant. I'm going to call it alpha. If I was to solve this properly, I would find a 1 and a 2. And to be technically correct, alpha can't be 0 because we don't allow for the 0 vector as an eigenvector. So this is properly doing, well, pretty properly doing the linear algebra to solve that. Although
just before you wrap it off, technically that should be equal to 0.
yes, well, I mean, this is the characteristic polynomial.
Yeah.
I want to know when that is 0.
Yeah.
So
Yeah.
this polynomial has these roots. So yes, we are looking for that equal to 0. So that would be the characteristic equation. This is just a polynomial. So yeah, technically I'm still right. Alright, so we have found one of the eigenvectors. Let's find the other one. And I'm going to be lazy again in solving it, just doing what I would do. I know there's only going to be one. The multiplicity of this root is 1. There's only going to be one linearly independent vector. So let's go for lambda equals 2. We consider, well, take this, subtract 2 off the diagonal, minus 2 is 2, minus 2, 1 minus 2 is minus 1. And actually this one is probably, I think it is a bit more important. I am going to do this properly as a set of equations. I am going to take row 2 and make it row 2 minus a half row 1, just so I can see it really is working. So you take away 1, take away half of that, you get 0, take away half of that, you get 0. It's also 0, again, it's good. I do have a solution, a non-zero solution. So hence, the eigenvectors for lambda equals 2 are, let's just call them different parameters, say beta 2, 1, no, not even looking. So the solutions to this, when you solve it, this just really tells me that these two numbers have to be the same, which is 1, 1. If you solve it a bit more slowly, you'll see the exact same thing. And again, I'm not going to allow beta to equal 0. Alright, so I have the eigenvectors. I have the eigenvalues, I have the eigenvectors. The final part is to just write down the solution to this equation. And this is just one of those things, you have seen this again and again about how you construct it. I'm just actually going to write down the solution. In a test, that's all I would want you to do is write down the solution. So using A, so using what we know, the solution to this, well, let's write out dx is, well, it's just going to be this vector, I like to write this out actually, equal to, well, it's going to be some constant, I'm going to call this A, times a typical eigenvector for that eigenvalue, which is 2, 1, e to the 3t, plus another constant, b, times this eigenvector times e to the 2t. And that's just for some constants a and b. For some, this is a and b. Alright. So there is probably something I would change before Daniel gets to this. You could also, I stated every single eigenvector possible for this statement. You don't really need to do that, you just really need to find one, I think. So personally I would be happy if you didn't have this parameter there. So
yeah, I'm okay with that. I would also not do row reduction for this.
yeah.
With the 2 by because you've got, so there's some comments on this in the chat. Another method of doing this for a 2x2, which is very straightforward, is taking any two of those elements, swapping them, and negating one. That's always going to be in the kernel, provided you've got the eigenvalues right. So for a 2x2 case, this is really straightforward to do. I can just look at this matrix and say, oh, 1, 1 is, maybe I'll point there, 1, 1 is going to be an eigenvector.
Yeah. The only reason I did this is I expect a lot of, well, a handful of people may find the wrong numbers. When you write this down, well, for example, here it jumps out at me immediately. Now I've done it right. These two have the exact same solution. I've gotten only one in the equation. It's not obvious straight away. I mean, it is fairly obvious that these two will cancel out like this. So there is something nice to maybe just, you write this down, stop for a second, think, is this going to have a solution? And, well, yeah, because this is a stage at which you can quickly catch that mistake, that's all.
Yeah, and this method will always work. Doesn't matter what your eigenvalues are, doesn't matter what the matrix is, this method always works. So there's a lot of merit in doing it that way.
Yeah, for the test.
I like the fast method for the test.
Yeah. Cool. Right. Cool.
Next question. Oh, and also we're talking about this in the chat. The fast method only works when you know that when you've got like n distinct eigenvalues in an n by n matrix. So you need to. Yeah. So be careful when using the fast method. If you've got, say, less than the full complement of possible eigenvalues, then you might need to then do it this way, because that way always works. There's some subtlety around the cases when you've got, say, repeated eigenvalues in your characteristic equation, or eigenvalues with repeated multiplicity in the characteristic equation. Okay. You've got some polynomials in the space of degree 2 polynomials. We're going to show they're linearly independent and explain why they're a basis. Okay, so there's going to be some row reduction here. I'm just going to throw these things straight into a matrix. You've got some choice here. You can either put the vector p1 as 1, 1, 2 or 2, 1, 1. And I'm going to put it in as 1, 1, 2. So that first entry in the top left-hand corner is a 1 because I like to work with that. So I'm just going to write it straight up, write it as a matrix, and solve it. This is pretty much how you would write P1, lambda 1 P1 plus lambda 2 P2 plus lambda 3 P3 equals 0, but I'm writing it as an augmented matrix. And now I row reduce. Zero, 1, minus 5, minus 6 is minus 5, 1, minus 4 is minus 3, 0. And one more row reduction to go. With 3. 0, 0, negative 3 minus 15 is minus 18. Yeah, minus 18. Hopefully I haven't made any mistakes there. Behold, 1, 2, 3 leading columns. This is in row echelon form. Please get it into row echelon form before you start doing anything rash, like saying how many solutions there are. Hence there are, well, hence there are unique solutions, but hence there are 3 So every leading vector is a linearly independent vector, and I have 1, 2, 3 linearly independent vectors. So all of these things are linearly independent. That's part A done. B. Explain why it forms a basis. Well, since this is the deal. If you have 3 independent vectors in a 3-dimensional space, that those vectors must span the space. So you might have seen a theorem like this in lectures. It pretty much says that if you have, well, there's really 3 theorems here. If you have 3-dimensional, if you have, getting mixed up with all my 3s, I'll just leave it at that. You have any 3 vectors in a 3-dimensional space, the space must be a basis, because it must also span that space. So maybe I'll write it, it must span. That's what the theorem says, it must span. Hence S is our basis. The only thing I'd be looking for in marking this question is that you've realized that there are 3 vectors in a 3-dimensional space, and these vectors are linearly independent. If you've written that down and concluded it's a basis, I'd give you the mark. Josh.
Now about that, I don't think you've written that down actually.
Any set of 3 linearly independent, thank you. Any set of 3 lin-ind. Yeah, any set of 3 linearly independent vectors. Thank you, Josh. In 3-dimensional space must span that space.
Yes, that's true.
Yeah.
So yeah, be careful with what you're writing down. Make sure you're including those conditions which are very important. Not just any 3 will do. Those 3 linearly independent ones will do. But yeah, so getting these straight into the columns. So that just became the first column. This is going to be something. You should even.
Hopefully they're familiar with that by now.
Yeah,
I don't want to write
working through the questions. This should be familiar to you.
Yeah.
So yeah, knowing how to start, that's good. Row reductions, good. You found 3 independent, and that allows you to prove all you need.
Cool.
There's just sufficiently many. Right.
Oh, can I do
Sure.
the catch-up question? No, wait, man, I will do it at the end, because I told everyone I'll do it at the end. Just, yeah. Sorry, as I was sitting down watching Josh, I did the question that we circled, but I'll save it till the end.
I believe there was another question requested in the chat.
Oh, yeah. From this paper or a different paper?
A different one. It doesn't look too hard.
Okay.
I looked at it, I believe I know how to answer it.
All right, cool. I think we might have time. It's only 2:10.
So this is going to be a probability question. In fact, these questions are always very wordy. It's so wordy, in fact, I actually haven't even written the question down up yet. This is just the information you need to answer the question. So let me just finish this off by saying, what is it we're actually going to be asked to do? So we have all this information. First question is, well, we just need to find the value of alpha. Doesn't sound too hard. And part B, find, and it's just going to be the probability of a bullseye. The probability that this archer will get a bullseye. Those are really what the last 2 parts are asking. So let's actually read the question. So we have a circular target, which is 2 meters round, and a bullseye with the same, well, the bullseye has a radius of 0.5 meter, and it's centered at the same place as the target. I'm going to just do a little picture to help myself, although it doesn't really matter very much, because the geometry here isn't important. You have a target, which is 2 meters wide, and you have a bullseye, which is only 0.5 meter wide. That's not actually important because we are given this probability density function. So we have x, a random variable, which is gotten by you fire your arrows, you measure the distance to that arrow from the center, and then you get this function. So, well, we're saying that all arrows hit the target, and so no arrow falls, it's always 0 outside of the target, and actually there are no negative numbers because you can't get any negative distance from the center. Alright, so we have this, and we're told that this is going to be a probability density function. We just need to really fit this alpha. We need to find what alpha makes this a true density function. I don't need to be worried about this thing being positive. The people who set this question up should have worried about that for me, so I only need to use one fact. So using I'll say the law of total probability, we must necessarily have the following statement being true. We must have that the integral from minus infinity to infinity of this density f of x dx equals 1. And, well, this is only defined over a very small range, so that is going to be the integral from 0 to 2, this quantity here, alpha x cubed minus 3x squared plus 4 dx equals 1. And this is not a hard integral to do. So what is this integral? Well, firstly, this is just a constant. Let's make my life easier by pulling it out. So now we have that alpha. Well, this integral is going to be, just do it, x cubed over 4 minus, well, integrate that, I get an x cubed over, sorry, not x cubed, x to the power of 4. This will go up to x cubed over 3, which will just cancel out that 3 and give me an minus x cubed, that works, plus 4 times x, and we're integrating from x equals 0 to 2, and that's actually quite nice because these all vanish, so all I get is alpha times, alright, so 2 to the power of 4 is 4 squared is 16, 16 over 4, or 4, minus 2 to the power of 3 is 8, yep, and plus 4 times 2 is 8, okay, well, that cancels, and this is just a 4, and we need that equal to 1, so 4 times alpha is 1, i.e. alpha must be 1/4. So that's my answer. To make this a proper probability distribution, I need to have alpha is 1/4. Alright. Now, I don't think I need any of that earlier information, so I'm just going to rub it all out and keep what I found. Right. Alright, so the next part of the question, so that was part A. Part B is, what is the chance, using this distribution, we actually get it into that bullseye? So probability of the arrow hitting the bullseye, bullseyes, no balls. So the chance of getting a bullseye, well, that only happens if I happen to get an x value which is within 0.5 meter of the center. So it's the same as firing my arrow and finding that this distance is less than, well, I'll say less than or equal to a half. Being a continuous distribution, actually, that boundary doesn't really matter. So, all right. So how do we calculate the probability of something being less than equal to half? Well, that is just the integral, in this case, from 0 to a half. Just anything within the range 0 to a half is good for us, of this density. I'll just write it down. So we know alpha now. Alpha was a quarter. X cubed was 3x squared plus 4 dx. No surprises there. That's the thing I just rubbed out, which will just be equal to, again, I'm going to pull that quarter out and get x to the 4 over 4 minus x cubed plus 4x from x equals 0 to a half. And we just need to calculate. So what is this? We get a quarter. Lots of powers of 2 here. So a half to the power of 4 is a quarter to this, is a quarter squared is a 16th. That will go to 1 over 32, 1 over 64. This will become a minus 1/8, and this will become plus 2. Well, that is the correct number, but I feel like I should try and simplify that at least a little bit. So it is a quarter times 1 over 64. Let's put this over 64 as well. So that means 64 is 8 squared, so 8 over 64. This will be 2 lots of 64 over 64, so plus 128 over 64. Helps to remember your powers of 2, which will be, so 128 minus 8 is 120, plus 1 is 121, over 64 times 4 is 256. And yeah, you are given a calculator in the test. I thought I brought my calculator, but did not. That is approximately 0.22 if I remember my calculations. So about 22%, no?
That's about half.
Oh, did I make a mistake? Let me just check my work.
Oh.
Actually, that doesn't remind me of the number I had last time I did my calculations. Well, I thought there was a 1 last time I did my calculations, but that definitely looks like a 2 to me. So yeah, I think I have made a mistake. So my previous calculations were wrong. I'll just leave it like that. But if you want to, you can find a decimal number for this. Give it as a percentage. But this is the correct number.
Yeah, as far as a marking criteria, so what happens with your exams afterwards is a bunch of us get together and decide how to mark something like this. You probably want it simplified like this, but you will have the benefit of a calculator in your exam. So you should be able to go easily from something like this to this. Yeah, we're not really testing your ability to add fractions.
Yeah. Okay. But yeah, so this is important. This is what you want. This is how you calculate it. This is the calculation.
But yeah, you will have machine assistance to get from here to here. Next question. Part C?
Part C is, does this provide evidence?
Okay, part C.
So it's just the usual question.
Does this provide evidence that
Toast is more likely to land buttered side up?
button side? Okay, behold, an experiment. 10 slices of toast. I'm going to put an underline under that, that's important. 10 slices of toast, buttered on one side, and they're all thrown. 7 of the 10 slices land butter side down. So 7, it's important. This is actually something they did on Mythbusters. In fact, I think this is exactly what happened in Mythbusters as well. Yeah, you have an experiment, 10 slices of toast. They're equally likely to land butter side up as they are butter side down. That's the hypothesis. We'll just assume that they're equally likely to. In fact, I think the question's here. What distribution can be used to model the total number of slices landing butter side up if each side is equally likely? Right, so here's all the information we need. There are 10 experiments. Immediately you should be thinking it's the binomial distribution. That's the distribution where there are a fixed number of experiments. And we want to know how many, or what is the probability that at least 7 land butter side up. So part A, binomial distribution, 10 events, each outcome is equally likely. So success being butter side up is the kind of event of success, and it has probability of happening 1/2. So you can just say X binomially distributed, 10 events, probability of success 1/2. Like that. This is a shorthand way of just saying this. You'll find that you end up doing a lot of these binomial kind of things, and this is just saying X is binomially distributed. You don't need to say any more than that. B. Calculate the tail probability of how unusual it is to see as many as 7 slices land butter side up. So this is the probability that X is greater than or equal to 7. Okay? It's the binomial distribution. You should know what this means. This is, well, so this here is the probability that X is equal to 7 plus the probability that X is equal to 8. So just breaking down the probability of seeing as many as 7 events, and using the fact that this is the binomial distribution, I can say exactly how much each of these things are. That's 10 choose 7 times 1, 2 to the 10. In fact, I might, well, I'll write it out this way. 10 choose 8. Plus 10 choose 10. Which is, well, I can take a common factor of 1 on 2 to the 10. And this stuff, I've forgotten what the sum of these things are. 10, 7, plus 10, 8. And you can just plug all this into your calculator. It ends up being about 17%. That's what I did. I just threw all this stuff in my calculator. It ends up being about 17%. Part C. Does this provide evidence that toast is more likely to add butter side up? The answer is no. This happens under the hypothesis that toast is equally likely to land butter side up or butter side down. You'll see as many as 7 slices landing up 17% of the time. That's not that unusual. So we'd say no. This is this. So I would say no. This is not a rare event. In Math 1A and in Math 1B, a rare event is something that happens with probability less than 5%. You can just take that as the benchmark. And this happens 17% of the time. So this is not rare. This is not like getting a straight flush in cards. This is something that happens 17% of the time, just ordinarily. So this is not something that's unusual. In Mythbusters, so I appreciate this is a bit subjective. 17% of the time may seem rare to you. And in fact, in Mythbusters, they said that this was rare, and they concluded from exactly this information that the answer was yes. But I think they just have a preference for drama. 17% isn't that impressive. I think in Math 1, in this course, you can take anything less than 5% as being a rare event. And it's the occurrence of rare events that make you start to question this hypothesis that toast is equally likely, the hypothesis that toast is equally likely to land butter side up or down. Josh?
Yeah. So no, I guess make sure you are dealing with the right distribution. Your assumption is that well, for this, you're assuming equally likely for the butter side up or butter side down. And yeah, and exactly, with that last one, just think about whether or not this strikes you as odd, and being odd means if the chance of it happening was less than 5%. That is exactly what we want in this course, the 5% benchmark. Other courses may do other things, but this course, 5%.
Yeah, if you're working on Mythbusters, 17%, that's fine. Cool.
Did you want to do your...
Is that the last one?
I don't see any more.
No.
No, there are only 4 questions on the algebra
I thought you had another one.
No.
No? Okay. My question. Okay, so this question was a request from the Math 1231 exam from last year. By the way, we've still got half an hour, so if you do have requests, just pop them in the chat and we'll get to them. So it's algebra, but it's a real step up from the kind of questions we've been doing. This is 1241 from 2015. Question 3, or part 3, question 4. You have a linear transformation P. P, I should say that P. P maps from V to V is a linear. So, I'm supposing P, this was part of the question that map from V to V, is a linear transformation. We need to show that the only possible eigenvalues are 0, 1. So this is a real step up from the kind of algorithmic things we're used to. You don't get to just throw in the characteristic equation anymore. You need to show through other means that the only possible eigenvalues are 0 or 1. Let So in this kind of question, you're going to have to resort to the definition. You don't have this algorithmic process anymore. You must use the definition. So we'll suppose V is an eigenvector, and we'll let lambda be its eigenvalue. Then P of V is equal to lambda V. That's what it means to be an eigenvector with eigenvalue lambda. This is something I can use with my definition of idempotent. Then, well, what happens if I apply P to both sides of this thing? P of V. On the one hand, that's P of lambda V, because P of V is just lambda V. I'm just applying P to both sides of this equation. And by linearity, I can pull this out as, well, maybe I'll say that this here is equal to lambda P of V. And this side here, well, I can use the idempotentness to say that this is equal to P of V. And remember, P of V, we know what that is. That's just P of V is lambda V. And here I get lambda squared V. so lambda, I can choose, this is true for any eigenvector. In particular, I can choose non-zero eigenvectors, and so lambda is equal to lambda squared, or lambda is equal to 0 or 1. There's only two solutions to this, 0 or 1. So the only possible eigenvalues are 0 or 1. That's not so bad. Part B gets a bit nasty. Well, maybe not nasty. But maybe a bit involved. Let's read it. Suppose that P is idempotent and that P is not the zero transformation and it's not the identity transformation. So here P is, the zero transformation is the thing that sends everything to 0, and the identity transformation is this thing that sends everything to 1. It's not that. Then show that P has both eigenvalues, 0 and 1. Okay, so this is a bit strange. We don't know the dimension of V. We don't know anything more about P than it's not 0 and it's not 1. How shall we answer this question? Well, let's start off with the fact that P is not 0. If P is not the zero transformation, then it must send a vector to something that's not 0. For some V not equal to 0, P of U, well maybe I say for some U not equal to 0, well no, some V not equal to 0, P of U equals V. If P is not the zero transformation, then it must map something to a non-zero vector. Only the zero transformation maps everything to 0. So if it's not the zero transformation, then there is something it maps to which isn't 0. Let's call it V. V is not 0. Okay. This is something I can work with my definition of idempotency. I can say that P of U is equal to P of V. Okay. And P of V. And I can work with this. This is equal to P of U by idempotency. And this is V. So P of V is V. V is an eigenvector and its eigenvalue is 1. Okay, so it was 5 lines, but they were a bit tricky, those lines. You start off just with this, as a consequence of this, there is some V that's not 0 that P will map to. Turns out that V is an eigenvector, and you can see that using the property here and the fact that P was idempotent. We do exactly the same trick, but now with the linear operation P minus I. So P is not the, maybe I'll change that to the, P is not equal to the identity transformation. For some U, maybe I'll rephrase it like this, just so it's very similar to the previous question. P minus I is not equal to the zero transformation. So just rephrasing it, we're pretty much going to replicate exactly that argument up here, but for the transformation P minus I. So there exists something which is not zero, some u, some u and v, such that p minus I of u maps to v and v is not zero. All right. Let's break this out into something where I can actually use my definition of idempotency. So p of u equals p of v plus u. Just rearranging this equation here into that. And this is something I can use my definition of idempotency on. I can start by applying p to both sides. So it's p of u equals p of v. And let's see, this, well, that's just p of u. This is p of v plus p of u. And let's see, p of u, that's p of v plus u. And this one here, p of v is p of v, and this I can leave as p of u. And then I can cancel that with that, and u equals p of u. That wasn't supposed to happen. No, I'll just leave that as, hang on. No, forget that. Okay. P of u is p of v plus p of u, and I'll cancel that with that, and therefore 0 is equal to p of v, and hence p of v is an eigenvector of eigenvalue 0. Otherwise known as the p is the v is in the kernel of p. Ha! That was a tricky question. Thank you to the person who asked it. Josh, this is a tricky question in 1141. So for all you people in 1241, for all you people in 1231, you won't get asked questions like this.
Yes.
Josh.
I mean, logic's all there. 1241 students, there's not really much I can say about this. You have to be able to sort of follow these arguments and reproduce them when needed.
There's probably lots of other ways of doing this. I have a preference for this way because it's actually quite constructive. You get the eigenvector. You get both times you end up with this eigenvector in your hand. So I kind of like this method. But maybe there's other methods more advanced. Or they may be faster methods than this, but even in the presence of faster methods, I have a preference for this.
Yes.
But that's just me.
I honestly can't think of any other methods right now. So there was actually a lot of chat, a lot of people asking for question 2 in the 1231.
Yeah.
One of the question 2s. I don't think we have time to answer all of them, but I could try and attack 1 or 2.
Yeah. Do you want to write it up and I'll answer that question from before?
Which question are you talking about?
The one that we circled from before. So you can start writing your question there, and while you're doing that, I'll just do that question from before.
Yes. That one.
Okay, so just while Josh is writing this,
let's suppose you've gone through your paper and you've got all the marks you can easily get. Now it's time to go through and get all those other marks that you struggled with for a bit. Recall, we had some complicated question with epsilon m thing at the front, but for part B we were asked just to show that some series converged. So I'll just remind you that given the AN and AN show that converges. Okay, and I'll just slip in. Was AN less than 1, or did you have to get that sum out of the way?
That's not guaranteed straight away. It'll
Okay.
be guaranteed at some point
Okay,
in the future.
okay.
So after some n value after that,
Okay.
you're guaranteed it's going to be
So,
small. But that's not given to you
Okay.
either.
so from part A, so we'll just assume the but from part A. From for all n greater than some fixed n, AN is less than 1. So we're splitting this into two. We're splitting it up to into the sum, this thing. We're splitting it first of all up to the first capital N of them, and then we'll take the rest. Good, so this is becoming two parts. This thing is just a sum of finitely many terms, and so it's finite. This thing we know converges, and I'll show you now. Yeah. So this part converges. It's just a sum of finitely many finite terms, so it's not a problem. This bit might be a problem, but because we've chosen n cleverly, we're going to use the comparison test. An is less than 1 for sufficiently large n. That means that an squared is less than an for all n greater than n. And this series converges because, by the comparison test. This is the sum from n. So the sum from n equals n to infinity of an squared is less than the sum from n equals n to infinity of an, which is less than infinity. So just by so this sum So, to summarize, we split this sum up into two parts. This is finite by just by the fact that it's finite in many terms. This is finite by the comparison test because we know each of those terms is less than each of those terms. Therefore, the sum of all these terms is less than the sum of all these terms, which is finite by assumption. So, finite number plus finite number is finite number, and the series converges.
Nice. I've been told my writing's quite small for this, so I'll read out exactly what this is. If you want to read the original text, it was 2015 1231 question 4 in part 4 of question 2, I should say. That's question 2, part 4. So this is a nice one to do. I actually will need the exam paper because I need.
This exam paper?
I'll need this. because there is extra information provided for the exam. You do have this table for the standard normal, and you do have some basic integrals, but I won't need those for this one. So I'm going to need this. So here's the question. Denver attempts an online quiz which has 50 multiple choice questions. So each one of these multiple choice questions has 5 answers, and only one of those answers is correct. And what we want to do is, let's let a random variable x be Denver's total mark. And so this is, if he sort of repeats the test again and again, just guessing randomly each time, this is a random variable. Now we're told we need to find the expectation of x and variance of x. This is more of a state what it is, actually. But we're not told what this distribution is. You're meant to, from the text, infer what type of distribution this is. So part A, well, this is actually just a binomial distribution with 50 independent experiments. Each of those has a 1/5 chance of success. So, first part is, well, the random variable x is distributed like a binomial distribution. So, alright, binomial, then there are n equals 50, there are 50 experiments, and each of those has a 1/5 chance of success. So maybe a little bit more wordy, I could just say, maybe I'll say this in words to be very clear. X is a binomial distribution with n equals 50 and p equals 1/5. So you're expected to know what the expectation and variance of a binomial distribution are. So the expectation of x, well, we know that for a binomial distribution, this is actually just n times p. It's the number of experiments times the chance of success. So that's 50 experiments, each of them has a 1/5 chance of getting the mark. That's a success. So our expectation is 10 correct answers. And the other thing is the variance. Well, the variance is quite nice. Again, this is just a formula you'll have to know. You wouldn't try and calculate this directly. You're expected to know that the variance of x is actually n times p times 1 minus p. Sometimes called q, I'm saying 1 minus p. So that is 50 times 1/5. And really, 1 minus p is really that leftover probability. It's going to be the 4/5. So it's what's left over from 1. And you can easily calculate this. 50 times a fifth we already did, that's 10. 10 times 4/5 is 40/5. So 40 over 5, which is really nice, it's 8. And so yeah, you need to know these formulas. That's really what you need to know. So know what distribution we're working with, know these formulas for the expectation and variance. Now the question says we want to use a normal distribution to approximate the probability that x is greater than or equal to 12, and that's where this table will come in handy. Right. So I think I may just have to rub this out and keep the information that's important. So expectation of x is 10, the variance of x is 8. And I can almost guarantee one of these questions will turn up on the exam because we don't want to waste paper printing those out, surely. Okay. So we want to calculate this. Probability that x is greater than or equal to 12. Now, I kind of think what I'm about to do is what should be the standard thing you do in the test is you should shift this slightly to take the half integer. So go halfway between whatever number you need to do to make this work. Maybe my brain's not working too well right now, so I'm actually just going to draw myself a quick picture. So we have 11, we 12, we have 13. What does it say? I want 12, so anything 12 or greater, I want to make sure I take this point and this point, so I need to slice down the middle there. So the probability that x is greater than or equal to 12, well, it's a discrete distribution. It's the same as the probability that x is greater than or equal to 11.5. So I haven't changed anything here, but this is sort of makes the answer a bit nicer, I think. Okay. So what I want to do, well, is I know that this, well, the nice thing about a binomial for a large number of experiments is it's kind of like a normal distribution. So let's just play around with this statement, make it look a little bit nicer. So firstly, I want to get rid of this mean, the expectation. So let's do that first. I'm looking at the probability that the difference between x and 10 is greater than or equal to 1.5. And that's equal to the probability that x minus 10 over, alright, so here's one piece of information I haven't stated yet. This is the variance. I don't really want the variance, I want the standard deviation. This is what you call sigma squared. So sigma is equal to square root, the variance is equal to root 8, or in other words, 2 root 2. So I want the probability that this this number here is greater than or equal to 1.5 over 2 root 2. Okay. Now I will actually just need to quickly grab a calculator, because I can't work this one out in my head. So let me just pull up my calculator. So I want to know what this number is, 1.5 divided by 2 root 2. Scientific mode, please. So if I've done this correctly, I get this is equal to the probability that x minus 10 over 2 root 2 is greater than or equal to, and I'm just going to truncate this at 2 digits, 1.06. Okay. Or maybe, just to be fair, it's approximately that. And the nice thing about this is, the way I set this up, this is approximately a normal distribution with mean 0, variance 1. I have a table which gives me all the information I need to know about that. So this is approximately probability that, well, that a standard normal, I'll just say z, is greater than or equal to 1.06. And that's just equal to the 1 minus the probability that z is less than or equal to 1.06. Which I can read that information off if I want to. So if I look at my table, I get 1.06 is 8554 minus 0.8554. A little bit of mental arithmetic tells me this is a 6, 4, 4, 1. So, sorry, I was reading that backwards doing my calculation. So I get a 0.1446, which seems to work. So about a 14%, well, 14.5% roundabout. Okay.
Cool.
Any
Great.
comments about that?
It's beautiful. It's perfect. I do want to. The stream just wanted me to say something about why you bust it back to 11.5.
Right.
So maybe I can back off. Yeah, I'll rub this off. So what we're really, so this is to address the question why we're using 11.5. So what we're really interested in is this tail probability
having something greater than or equal to 12. So there's all these kind of 13, 14, and so on. The binomial distribution looks like this. It's got all these discrete boxes of finite height, and the height here is the area of this block is the probability of x being equal to 12. What we're interested in is the area under all these blocks. That's the probability that x is greater than or equal to 12. So this one is probability that x is equal to 12, and so on. That's what we want to know, but it's a bit difficult. So instead, we use the normal approximation. Now, if you choose your normal approximation, if you shift it along and then divide by the standard deviation, then you end up having, well, I should say, I'm going too fast. This curve here is the probability density function of another variable. Let's call it y, which is the normal distribution, not the binomial distribution, but the normal distribution, which has the same expected value and the same variance as the binomial distribution. So if x is binomially distributed and p like that, then y is normally distributed, and the density functions are kind of related by this. So the probability density will go through the continuous random variable will approximate the discrete random variable like this. So in order to get the best possible approximation, what you need to do is actually go all the way back to 11.5 here, because the area under this curve, is a good approximation for the area of these boxes. But it's best when you take it back to 11.5. I don't think I've explained that very well.
Well, I mean, the way I think about it is you're just trying to collect all the probability between up to within sort of whatever's the closest integer. So everything that's closest to 12, I'm just collecting onto 12.
Yeah.
That's the way I sort of think about it. So if you're closer to 11, I would assign all that probability to 11.
Well, let me try this again. You want to figure out something from a discrete probability, but you're using its continuous, a related continuous probability to get at it. So really, I would have changed this actually, because here it's a discrete probability, and maybe I could change this to y. So there's really two approximations going on. One is where you approximate a discrete probability with a continuous probability, and that's what's going on here. So the probability that x is greater than or equal to 12 is quite similar to, or approximately, the probability the continuous random variable y, distributed like this, is greater than or equal to 11.5. And then, as a continuous random variable, see, this is the normal distribution, but with the funny expected value and variance. And what Josh does here is he arranges it so that this is actually the normal distribution. See, the normal distribution, all normal distributions are the same. They just they have a different variance, they have a different expected value. And we have a table for the normal distribution on 0, 1. So what Josh has done is taken a normal distribution and then slowly molded it so that it has the correct variance, and so it has expected value 0 and variance 1. That's what these operations do. He shifted the expected value over, so the expected value is 0, and then he divides by 2 root 2, so the standard deviation is so the variance is 1. And then you've got this variable here is z, and you can look it up in your anything. I probably explain this better in the notes, in my notes in chapter 4.1. So if you want to read, I've written a few pages on this in my notes if you want to read them.
Yeah, so I think he's right. I introduced the continuous one a little bit too late. I also double-checked. This was striking me as kind of weird because the standard deviation, if you look at it, was about, well, 2 times root 2 is kind of like 3. This is definitely not going to be, if you're 1.5 away, you're not up to even the first standard deviation. So yeah, I went back and checked. I made a mistake.
Okay.
So it was actually a large probability than I thought.
Yeah, so this is somewhat subtle, and it probably takes a whole lecture to explain this. If you want to look up my lecture notes, it's the last set of slides in my lecture notes. But your lecturer probably has this stuff, covers this stuff as well. Anyway, that's enough from us. It's time for a horse race.
Right.
Josh.
So it's the race that stops a live stream.
Sorry?
It's the race that stops a live stream.
Yes.
And a nation. Okay, so thank you for joining us. I hope you got some help out of this.
Yeah, and thank you for joining us in Mathematics 1A and 1B. It's been our pleasure to teach you math in these live streams and elsewhere.
Yes.
So
hopefully maybe we'll see you around the maths department sometime.
yes, and good luck in your final exams.
Yes.